Dear student, Assalamu alaikum. Auzu billahi minash shaitanir rajim. Bismillahir rahmanir rahim. My name is Dr. Muslim Khan, Assistant Professor, Department of Chemistry, KUST. Today, the topic of our presentation is interpretation of IR spectra. And today is lecture number 26. Course code is CHEM451, and we are discussing getting some information from IR spectra and molecular spectroscopy. First of all, to discuss the spectrum interpretation process, suppose that we have done an experiment. We have subjected our sample to the IR spectrophotometer. So we are getting a piece of paper that is called spectra. So what type of information basically we can get from IR spectra? So from where we are starting to interpret or to get this information. First of all, to recognize a pattern in an IR spectra. Then the association of this pattern, which we recognize it in a step number 1 with some physical parameter of the sample. So first of all, recognize the pattern in a spectra and then associate this recognized pattern with some physical parameter of the analyzed sample, and then identify possible meanings, means a purpose explanation. So what you want to extract from the spectra, then identify those possible meanings, what you want to extract from the IR spectra. So once a spectrum is obtained, I want to summarize. The main challenge is to get this purpose explanation from this spectra, to extract the information it contains in abstract or hidden form. This requires the recognition of a certain patterns, and then association of this pattern with physical parameter, and the interpretation of these in terms of meaningful and logical explanation in science. In IR spectrum, like whenever you see the IR spectrum, basically there is not an absorption mode. So what happened in IR spectroscopy, that you are subjecting your sample into the IR spectrophotometer. This your sample absorb some of the IR radiation. It means that the rest of the radiations are transmitted. So basically in IR spectra, you are measuring that absorbed radiation. So the IR spectrum, when we see it in absorbed form, is a plot of transmitted radiation or absorbed radiation versus the intensity of the transmission or absorption. Frequency appear in axis in unit of inverse centimeter, and intensities are plotted in the on the y-axis in percentage units. So this graph shows a spectrum in absorption mode. Suppose that this is from 0 to 100% absorption of IR radiation. So this is the noise of the instrument, and it will go like this, and whenever it this sample absorbs something, it will show this intensity of absorption and will show the peak in that specific wavelength, wave number region. And this is usually you see the IR spectra in this mode. So in IR spectrum, when they are in a transmission mode, so when this is you are putting the transmission of the sample, which is like 90%, usually we take it 100% for blank. So it will show like this. And when some of the transmission is decreasing, it means that absorption is increasing. So this is giving you the information that this sample is absorbing, or means less transmitting. It means that somewhere it is absorbed. So this graph shows a spectrum in a transmission mode. This is the most commonly used representation and one found in most chemistry and spectroscopy books. Therefore, we will use this representation of IR spectrum in our this presentation. So this is classification of IR bands. That IR band can be classified as a strong band or medium band, showing here. This is a medium, this is a strong, and this is a weak band, depending on their relative intensity and infrared spectrum. So there are three types of band in IR spectrum. So a strong bands basically cover most of this y-axis. You can see here, this is a strong band which is covering more of this y-axis in a transmitted mode. A medium band like this one, this cover almost the half of the y-axis from here till here. You can see like almost half of the y-axis, while a weak band usually falls to about 1/3 or even less than y-axis. So these are classified in this way. So infrared active bonds, not usually all the covalent bonds display bands in IR spectrum. Only polar bonds do so. These are referred to as IR active bond. Some of the bonds are not IR active. Some show a very weak band and some shows medium and a strong band. Okay, so not all covalent bonds, display bands in IR spectrum, but some shows. So not all covalent bond displays bands in the IR spectrum. Only polar bond do so. These are referred to as IR active compounds. The intensity of the band depend on the magnitude of the dipole moment associated with bonds in question. Strongly polar bond like this is a carbonyl group produce a strong bands, while medium polar bonds are and asymmetric bonds produce a medium bands like this, and weakly polar bond and like symmetric bond, this is a symmetric bond, produce weak or non-observable bands. Infrared band shape. So while interpreting the IR spectra, you will see some of the bands are narrow in shape and some of the bands are broad. So infrared band shape come in various form. Two of the most common are narrow and broad. Narrow bands are thin and a very pointed bands like dagger, while broad bands are wide and smoother. A typical example of a broad band is that displayed by OH bonds, such as those found in alcohol and carboxylic acid, is shown below. Like this is the example of a broadband. So here you can see that these broad bands are wider and smoother, while in comparison to this one, like this is the typical example of band of OH bonds, which are found in alcohol and carboxylic acid. So what type of information basically we can obtain from IR spectrum? IR is the most useful in providing information about the presence or absence of specific functional groups. IR infrared spectra can provide a molecular fingerprint that can be used when comparing samples. If two pure samples displays the same IR spectrum, it can be argued that they are the same compound. It means that they will give you the fingerprint of the first spectra means similar, so it means that they are same compound. IR infrared does not provide detailed information or proof of molecular formula or structure. It provides information on a molecular fragment, specifically functional groups. Therefore, this IR spectra is very limited in scope, as I told you before in my before lecture, that it must be used in conjunction with other techniques to provide a more complete picture of the molecular structure. So this is the IR absorption range, means where does most of these compounds do absorb IR radiation. The typical IR absorption range for covalent bond is from 600 to 4000 centimeter inverse wave number. This graph shows the region of the spectrum where following types of bond normally absorb. This is the region from till 1400 is known as a fingerprint region. So for example, a sharp band around 2200 to 2400, this is 2200, 2400, would indicate the possible presence of carbon-carbon triple bond or carbon-nitrogen triple bond. So this gives you a clue. While usually nitrogen-hydrogen showing the absorption in between 3300 to 3400 or 3500, while oxygen hydrogen between 3000 to 3300, while carbon and hydrogen showing from 2700 till 3100. Although the entire spectrum can be used as a fingerprint for the purpose of comparing the molecule, the region from 600 to 1400, from here till here, range is called fingerprint region. This fingerprint region is a complex region and it is very difficult to interpret peaks here found in the fingerprint region. This is normally a complex area, as I told you, that are showing many bands, and here you can see, frequently overlapping each other. This complexity limit, it's used to that of a fingerprint and should be ignored by the beginner like you student when analyzing the spectrum. As a student, you should focus more your analysis on this region of the spectrum, that is to the left of the 1400 centimeter inverse until 4000 wave number. So the reminder of this presentation will be more focusing on the IR identification of a various, as I explained the fingerprint region, and I explained the spectra in absorption mode and transmission mode. So the reminder of this presentation will be focused on the IR identification of different functional groups such as alkene, alcohol, ketone, carboxylic acid, etc. This is the example of IR spectra. So that usually we are examining this IR spectra. That this is a fingerprint region, and this is the region where most of these compounds showing absorption. So this table is very important. I already discussed this table in one lecture, but is interpreting the spectra just to refresh your knowledge, I give this table in this lecture as well. So here is the bond. Here you can see carbon hydrogen bond, which is in the alkane. This is usually showing in the frequency range of 25850 to 2970, and this is usually showing a very strong band. So this is the carbon hydrogen, but carbon hydrogen not of alkane, of alkene. This showing 3010 to 3095 and is usually giving a medium band. While this is carbon hydrogen of alkyne, this showing the is in the range of 3300 and is showing a very strong band. Coming to the carbon hydrogen of aromatic ring, showing the absorption in 3010 to 3100 and it's showing a medium absorption. While oxygen and hydrogen, monomeric alcohol, phenol, hydrogen bonded alcohol, phenol, monomeric carboxylic, hydrogen bonded carboxylic acid, showing a frequency absorption in this frequency range, and intensity is variable, sometimes broad for this, and for this one medium monomeric carboxylic acid, and hydrogen bonded carboxylic acid broad and in this region. Similarly for amines, amides, alkenes, for aromatic rings, alkynes, amines, amide, nitrile, nitriles. So all the region is given here and the intensity is given here for these bonds. So while interpreting different spectrum, alkane have no functional group. So that organic compound which is having a single bond in between the carbon, so their IR spectrum display only carbon-carbon, carbon-carbon and carbon-hydrogen bond vibration. Of these, most useful are carbon-hydrogen bands, which appears around 3000 frequency centimeter inverse. Since most are organic molecule have such a bond, most organic molecule will display those bands and their structure. This is IR spectrum of alkene. Beside the presence of carbon hydrogen bonds, which is showing this carbon hydrogen bond showing stretching vibration in the 3000 region, alkene also show sharp medium bands corresponding to carbon-carbon double bond stretching vibration about 1600 to 1700 centimeter inverse. This is 1600 and centimeter inverse. This is due to the exact 1642 due to the carbon-carbon double bond. So sometime alkene might also show a band for this double bond and this carbon hydrogen bond. This carbon hydrogen must be different than alkane, than carbon hydrogen of alkane stretch. appearing around 3080. So 3080, this one is shown below. However, this band could be obscured by the broader band appearing around 3000 centimeter and worse. So so this spectrum shows that a band appearing around 3080 can be obscured by a broader band appearing around. So this is quite broader. This way it can be obscured. So the most prominent band in alkyne correspond to carbon-carbon triple bonds. It shows a sharp, weak bands at about 2100 centimeter inverse. The reason it's weak is, why it is weak? Because the triple bond is not very polar. In some cases, such as highly symmetrical alkyne, it may not show, it may not be observable. You can call it non-observable, all due to the low polarity of the triple bond associated with those of alkynes. Terminal alkynes, such as one propyne, one pentyne. That is to say, those where the triple bond is at the one end of a carbon chain, having carbon hydrogen bonds involving the sp carbon, having sp hybridization, the carbon that forms part of the triple bond. Therefore, they may also show a sharp, weak band at about 3300 centimeter inverse, corresponding to the CH, a carbon hydrogen stretch. Internal alkynes, that is those where the triple bond is in the middle of a carbon chain, do not have carbon hydrogen bonds to the sp carbon and therefore lack the aforementioned bands. The following slide shows comparison between unsymmetrical terminal alkyne 1 octane and symmetrical internal alkyne 4 octane. This is the comparison of 1 octanes and 4 octanes. So here you can see carbon-carbon stretching. This is a symmetrical. This is for unsymmetrical, and showing this bond stretching at 2119 due to the carbon-carbon triple bond, while this is missing here in this spectra. And this one, this is present in both of the 3000, both of the spectra, but here this stretching is due to the carbon attached to the triple bond and hydrogen, that is 3313, while this is missing in this 4 octane. So IR spectrum of nitriles, in a manner very similar to alkyne, nitrile show a prominent band around 2250. This is caused because of the carbon nitrogen triple bond. This band is a sharp, you can see it, very sharp band, pointed shape, just like the alkyne carbon triple bond, but because the carbon nitrogen triple bond is more polar, this band is a stronger than an alkyne. This is a stronger than alkyne, showing 70% of the absorbance, and while in alkyne it is little bit means it is a medium one, not a very strong one. So this is how to differentiate the stretching of this carbon nitrogen from the carbon triple bond. This is the IR spectrum of an alcohol 1-butanol. The most prominent band in alcohol is due to the oxygen hydrogen bond, and it appears as a strong broad band covering the range of about 3000 to 3700 till here. So the shear size and broad shape of the band dominate the IR spectrum and make it hard to miss. Means this is quite common for alcohol, that it is covering from 3000 to 3500. It is quite broad, it covers most of this region, so therefore it is very hard to miss that alcohol is present in this sample. So IR spectrum of aldehyde and ketones. Carbonyl compounds are those that contains the carbon oxygen functional group, carbonyl functional group. In aldehyde, this group is at the end of carbon chain, while in ketone it may be present in the middle of the chain. So as a result, the carbon and carbon oxygen bond of aldehyde is also bonded to another carbon atom and a hydrogen, whereas the same carbon and ketone is bonded to the two other carbon atom. Therefore, aldehyde and ketones show a very strong, a prominent stake-shaped bands around 1710 to 1720, right in the middle of the spectrum. This band is due to the highly polar carbon oxygen bond. Because of its position, shape, and size, it is hard to miss. Because aldehyde also contain carbon and hydrogen bond to the sp2 carbon of the carbon oxygen double bond, they also show a pair of medium strength band position between 2700 to 2800. These bands are missing in the spectrum of ketone. This is the biggest differentiation between ketone and aldehyde, that this carbon hydrogen band in aldehyde is present, while in ketone it is missing, because ketone, the carbon attached is a carbon of double bond, carbon and oxygen is attached to the other two carbon atoms. These bands are missing in the spectrum of ketone because the sp2 carbon of the ketone lacks the carbon hydrogen bond. The following slide shows a spectrum of aldehyde and ketone. Study the similarity and the differences so that you can distinguish between two. Here is the example. Like this one is butyraldehyde. Carbon attached to the oxygen with double bond, but at one terminal of the carbon, this is attached to other hydrogen atom. While in ketone, this is 2-heptanone. This, the same ketonic group, this same carbonyl group is present in the aldehyde. This is attached to the two other carbon atoms. So what is the difference between these? So till here, the spectra is quite similar. You can see it. The spectra is quite similar, but the difference is here. Here, this carbon hydrogen stretch. Here, this stretch is present. This is in aldehyde, while this stretch, you can see this fingerprint, this region is not present in the ketonic group. So that's why it is quite like here. It is showing 1718, 1720. So this is quite similar of aldehyde and ketone, but the difference is here because hydrogen is attached to this carbon atom and here other carbon is attached. So the environment of these two carbon is different. So these are different. IR spectrum of carboxylic acid. Carboxylic acid functional group combine the feature of alcohol and ketone because it has both the OH bond and carbonyl bond. Therefore, carboxylic acid shows a very strong and broad band covering a wide range between 2800 from here 2800 and till 3500. This is typical for carboxylic acid because this is both for carbonyl and for carbon hydrogen bond. So at the same time, they also shows these carboxylic acid show a very strong and broad band covering a wide range between 22. This one at the same time, they also shows the stake-shaped band in the middle of the spectrum around 1710, corresponding to carbon, just like similar to the ketone. IR spectrum of amine. The most characteristic band in amine is due to the nitrogen-hydrogen bond stretch. It appears as a weak to medium. Somehow, this is nitrogen-hydrogen stretch. This is weak are medium, weak to medium, somehow broad band, but is not a broad as oxygen and hydrogen band of alcohol. This band is positioned at the left end of the spectrum here, this one, in the range of about 3200, like from here till here, 3200 to 3600. Primary amines show two nitrogen-hydrogen bonds. Therefore, they typically show two spikes. Like here, this is one spike. They shows two spikes that make this band resemble a molar tooth. Secondary amine have only one nitrogen-hydrogen bond, which makes them show only one spike, resembling a canine tooth. Finally, tertiary amine have no nitrogen-hydrogen bond, and therefore this band is absent from IR spectrum altogether. The spectrum below shows a secondary amine. This is IR spectrum of amides. So the amide functional group combined the feature of amine and ketone because it is both nitrogen hydrogen bond and carbonyl bond. Therefore, this will be the mixture of both nitrogen hydrogen and carbonyl group stretching. So thank you very much for today's lecture. And for these lecture, you can use this JD question, instrumental analysis, Douglas, Scooch and West, Scooch and Crouch, principle of instrumental analysis, and B. Wells, atomic absorption spectroscopy. And thank you very much.